Welcome to Lecture 6. In this lecture, we are going to introduce three linear time sorting algorithms, namely the counting sort, the radix sort, and the bucket sort. Each of these methods will require some assumption on the input so that the overall sorting time can be done faster. Let's start with the helping the billionaire problem. So Bill here is a billionaire and he has a super big wallet. Inside his wallet, there are banknotes of one of the following 9 types. So there could be $1 notes, $5 notes, $10 notes, and so on and so forth, up to $1,000 notes. So all these notes could be there. And the wallet is so big that there are n notes in total. So we want to sort all the notes in the wallet quickly. So how can this be done? So we have studied merge sorts before. So merge sort works in order n log n time. So this can be done in order n log n time. But for this problem, we can do faster. So what we can do here is, let us prepare 9 bins, one for each type of nodes, like this. What we are going to do here is, we are going to process the nodes one by one, and then we put each into the corresponding bin. So when we see a $1 note, we put it in $1 bin. When we see a $10 note, we put it in the $10 bin. Once all the notes are processed, we will collect the notes in each bin. But we start from the $1 bin and then $5 bin and so on and so forth, according to the value of the notes in the bin. In this way, we can sort all the notes in order n time. Now notice that in the previous method, there are no direct comparisons between the nodes, but we still can sort the nodes in the end. The reason here is that we have actually looked into the values of the nodes and used the value to distribute the nodes into the correct bins. Although we are not comparing the nodes, we are comparing the bins. And then when we compare the bins, we have made indirect comparisons among the nodes inside these bins. Now this idea is actually what counting sort works. So in counting sort, we are sorting n items. Each of the item is chosen from one of the k classes. And the n items are assumed to be in an array A initially. And the method works like this. We are going to count the number of items in each class. So that's why we call it a counting sort algorithm. So to count. After that, we will assume that in the final result, A will be storing the sorted of the n items. So in that case, we will calculate the positions in A for each class when the items are being sorted. And finally, we will put the items to the correct positions in A. So let's see an example run. So this is the case that what happens before running. A is the array that is storing the input items. Items are chosen from class 1, 2, 3, 4, 5. And then we will be using an extra array B to hold the temporarily sorted results. So we are going to use B to help us. So initially, we set the number of items to be 0. But then what we are going to do, we will scan A from left to right so that we can get the correct count of each of the class. So by scanning A, so we will see 2, then we increment the counter for 2. When we see 1, we increment the counter for 1. So in the end, we get the correct count for each of the class. And then what we are going to do here is we are going to calculate the positions. So for class 1, it starts at position 1. Now class 1 has 2 items. So in that case, this implies that class 2 will start at position 3. Now, class 2 has 3 items, so this implies class 3 will start at position 6. Class 3 has 2 items, so this implies that class 4 will start at position 8. Now, class 4 doesn't have any item. So in that case, we will see that class 5 will also start at position 8. We don't actually need to care about class 4 anymore because it doesn't have any item. So actually, we will ignore it in the end. And then, so after that, we have already computed the positions, the starting positions for storing each class of items. And once the positions are known, then we are going to put the items into the correct location. But we are not going to put it into A directly, we will put it into B first. So here, in this array B, we have already marked the positions, the starting positions that we are going to put for each class of items. So one for class 1, so it is pointing at position 1. For class 2, it is pointing at position 3. Class 3, position 6. Class 4 and 5, position 8. What we are going to do here is we are going to scan A again from left to right. So this is what we do. So when we see this item 2, then we know that we are going to put this into the location that is for class 2. So we are going to put it here. So in that case, we will set the third position B3 to be equal to this number 2 and also update the position here so that by the time if we ever see another item from class 2, we know where it should be put. After that, we see 1, so we will put this item here and move the pointer. And we see 2 again, so we will put 2 here and move the pointer. We see 5, we will put 5 here and move the pointer. Yeah, it really doesn't matter that the pointer is pointing out of this bound because we know that there is no 5 anymore. For 3, we will put it here and move the pointer. Another 3, we put it there and move the pointer. A 1 here, we will put it here and move the pointer. And 2, we will put it here and move the pointer. So very, very, very simple, right? So this is how counting sort works. Now finally, we have the B here. So B is actually a temporary array. We are going to put all these items back into A. So we have a copy step. So after copying B back to A, we are done. So A now will contain all the original items, but now sorted. Now, counting sort runs in order n plus k time. So it is not actually really linear, but there is a k term here. So why there is a k term? First of all, k is the number of classes. So here, we will see that there are many places that will involve k. So first of all, the creation of this table, there are going to be k classes. So there are going to be k counters and k positions, right? So in that case, it takes order k time to initialize, to prepare this table. And after that, yes, then we are going to process the items one by one, and then this part is going to be simple. So this part will simply take order n time. So we are going to use k time basically in initializing the counts and also the positions. Okay, so when k is big O of n, so normally the number of classes is a constant independent of n. So if this is the case, let's say k is big O of n, then the running time now truly becomes linear. Now, one more thing to mention here is that counting sort is a stable sorting algorithm. So stable sorting is a property of sorting algorithm, meaning that items with the same value. So usually sorting, we are going to compare items that have different values, but sometimes we may have items with the same value, just as in the previous example. And then items with the same value, if they appear in the same order before and after sorting, then if this is true, then in that case, if it is guaranteed to be true, then this sorting method is called stable. Okay, so let's see this example. So for instance, there are a couple of 2s here. So we have before sorting, the red 2 is before the blue 2, and this blue 2 is before this green 2. And after sorting, this red is before the blue is before the green. And if it is guaranteed, it works for each of the items with the same value. So 2 works, 1 works, 3 works. It's not just a coincidence, but it is guaranteed to work for every input. Then in that case, the sorting method is called a stable sorting algorithm.